because that's also on, I think. No? Both are on.
Talk like this.
Okay.
Very loud.
Else, he's been on a round robin tour of India, going all around talking about the work he has been doing. Professor Virendra Sharma come from University of Miami. He's working on many different things. Interesting overlap with some of us here is he looks at occurrence and remediation of various pollutants, specifically with oxidated molecules systems. His work involves quite a lot of using MOF and COF and various different elements. So there is some overlap of that here in ICWaR also. He's been a fellow of many academies. I think I can't read all of them, but many is a member of Academy of Europea, is a fellow of AAS, ACS, EuroAS, ASC, RSC, distinguished honor Humboldt Award, Abdul Aziz International Prize for Water, various different things. So it's very interesting. Please, Mr. Virendra, please tell us about the work which you have been doing, especially related to high-valent.
Thank you very much, Praveen. Appreciate having me here and kind introduction. One thing is, he mentioned I'm member of many academies. The most important academy is Indian Academy of Science, which I'm not. So I required them to nominate me. So I become an academy member of Indian Academy. So that's very important in my life. There are many front, some seats are there, so you're welcome to come. Normally students sit in the back. They they think I don't ask questions to them, but that doesn't work this way, right? And you're supposed to ask questions, especially students. If you don't ask questions, what is going to happen? I give exam, I carry big bag. Okay, so please ask questions, the student. And so, so to introduce. Yeah. Okay. So this just to introduce my university. I'm from you see Miami. Miami is actually known for something else, but the university exists there too, and where I did my PhD too. So I had a very difficult time doing PhD in Miami because more difficult was because my lab was just on the beach. I did marine school. So really I had tough time to finish my PhD there. And this is our university completed. Who are only. So my university became member a couple of years ago. You don't kick you out. So you still need to maintain the ranking. Football is very famous in my university, and some of you already know. Yesterday, Saturday, we have won the game against my previous institution very quickly because I didn't like that institution, Texas A&M, and they beat Texas A&M. Aggies by Hurricane. The Hurricane is the team name in football on Saturday. So we went to quarterfinal in college football now. And we have aerosol science center, science and technology, and they are top 5. They are very good. We have 5 academy members, and deal for the university because that determines the ranking. It's off here, right? So, and I can hear no problem, and they can send me. Okay. This I wish or pray that I so I want to keep working. And once you become a member, they don't get rid of you easily. Okay, that's because if you're not member, then they say bring money, otherwise go home. Okay, so I'm praying a lot in this visit that I became member of academy. So I request all of you to pray for me too. And this is I really joined. I remember you can see here, Dr. Uh, he's and they recently hired me to that credential. Other important thing is to get a word. Okay, so people they want to get rid of it, they make a coordinator of those program, master student program. Like they made me coordinator. Okay, so I'm very careful. So I tell you, if anybody is out there interested in master program, please apply. Okay, especially we need rich one because we need to pay. But PhD is free. So this is kind of one way of going to PhD. You go for master, then you convince the others to take you, other professors, right? And then it's free. Tuition is free, assistantship is free, and top of that is Miami. Okay. Okay. So I request you to advertise. So this 90,000, then became issue of antibiotics. Nanoparticle was issue. I paper on nanoparticles, my carrier, silver nanoparticles, then toxins, and then microplastic, nanoplastic, and PFAS that current interest. So not only studied chemistry of those pollutants, I also look for the solution. An advanced material. If you say smart, people pay attention. So I just write, okay? No like smart. And photo oxidation reduction. You can we study the arsenic, solar light, and RNA more than 35 years. Okay, like I have nothing else to do. It's true, I have nothing else to do. Also studied organic framework, which got the Nobel Prize recently. So I will not get Nobel Prize now. So they already gave the Nobel Prize, metal organic. Covalent organic framework, and then single the latest one. Sadly, the young one I like to convey. This is my interpretation. What are the challenges in water treatment? Okay, this is AOP people use to get rid of pollutant, advanced oxidation processes that produce many radicals and to attack those pollutants. Okay, so that's what we do. We study in the lab, study one pollutant and see, and we show it's quite efficient. Okay, but when you go to the real environment, it doesn't work because real water contains many ions, major ions, molar higher concentration. Okay, and there is reason I put in the light there different color of pollutant, pesticide, personal care products, industrial chemical toxins, because they are very low concentration. So what is going to happen? Those radicals will be consumed by these major ions. These two we like to remove. This is the real challenge. How you can do advanced oxidation processes. And then they produce secondary radicals after reacting with the whole act with oxygen very fast. So we use micromolar or less nanomolar pollutant in presence of major ions. Clear, this is a problem. Okay, and we do a lot of advanced oxidation process. After Honda and Fukushima give the water splitting in 62, they produce radical people have been studying. In 62, if you really see, there's not many applications. Titanium dioxide people publish left and right. But then there's still no real application, very few, especially cases in Spain or maybe some other country. Okay? And this is the reason I think. And NOM, natural organic matter, which are already present there, formic acid and humic acid. And other thing people do it because they have been doing AOPs, oxidation, they always use oxidation, no matter what problem is. Let's apply AOPs. For some cases, we don't need AOPs. We don't need oxidation. We need reduction, especially fluorocompounds. These are fluorocompounds. CF bond doesn't go anywhere with the OH radical or AOP. It needs reduction. Okay? But we're still using AOPs. And so we need advanced reduction process. And reduction is done by hydrogen electron, sulfide radical, or some radical that carry reduction. But in reality, this hydrogen electron or sulfide easily captured by oxygen. So fast reaction. And oxygen is much more concentration than your pollutant. So again, your method will work if we have no oxygen around. Where is that in a real environment where is no oxygen? Maybe down somewhere in groundwater, but that's not practical either. Clear? These are the real challenges. So I'm trying to solve, or at least I think, I will solve this problem. You are the judge, okay? Not me. And how I'm going to propose now today, instead of using this radical species or reactive oxygen species radical, let's start using high-valent metal species. Okay, like 6, 5, and 4. Okay, or manganese ones. Why I am proposing this to do? Because they don't react with these things to be captured. They can still attack these. This is the one reason. They resist the matrix components. Point of view, your chemist here, we have around these, they start behaving differently, and differently in the sense even better. And that if we have carbonate around, high-valent iron even react better. And that's the reality. So that's why I want to propose high-valent iron species. And they can also perform multiple actions. Can perform redox, coagulation. But by the way, you can ask me question anytime during presentation. Don't have to wait till the end before I give the exam. Okay? Clear? So please raise your hand and ask questions. So I'm going to convince you today, yes, high-valent iron is the way to go. And when I say it can do 3 things together in one cycle, oxidation, it can remove antibiotics or any other pollutant will require oxidation. It can do dissolution, bacteria it can remove. It can do coagulation too, because RN6 goes to RN3 form, final form, that can coagulate some of the metals like arsenic and some other toxic metals. And I'm going to give examples of each one. First example is arsenic. Arsenic is naturally present, which is why arsenic 3 is present in neutral species, ASOH3, that you can see. Neutral, it will not interact. If something doesn't interact, it will not work, right? Efficiently. So RN6 can immediately convert to arsenic 5, and then this RN3 form hydroxide. This hydroxide then co-precipitate arsenic, and you can remove arsenic. That you can see. And if you're looking for funding, supply, you need to create this kind of figures to scare people, right? It will create cancer. It does create cancer, by the way. I'm not making up, okay? So then people give money when they're afraid of it, okay? So not only arsenic, we can also remove other metal ions too. Here is showing cobalt, nickel, copper, cadmium. So we were interested also looking for mechanism, how that works. Because mechanism is also important, because once you remove metals from the water, you have a sludge, right? On hydroxide sitting there. What to do with that? What they do is they take to some landfill or somewhere in the field. That's common practice all over the world. But then it can go back to the water, right? So you want to capsulate in the lattice so it doesn't get released easily. And that what we try to demonstrate. Some of the metals, they can go lattice of iron oxide, so it doesn't get released. So that's the mechanism this paper is talking about too. Lead is a big problem. They still use lead 5, significantly high numbers. And it creates lead, soluble lead in lead. That time there, so now the money to replace, and political did not fly that. spend the money. It, lead oxide organic matter reduced lead 4 to lead 2, and you can see soluble lead there. Okay, but if you can see it's very much less. So ferrate can help to reduce the soluble lead in water. That I'm trying to convey. Not only metals, but other kind of metal like lead can also be. And now I'm going to give the example of disinfection. Okay, disinfection, and ferrate behaves better than chlorine. Historically, chlorine is disinfection people use. Okay, and chlorine doesn't work for everything because chlorine is around for a long time. So bacteria are very smart. Really, to me, it's very fascinating. They know how to save themselves from chlorine now. They adapt. That's called antibiotic resistant bacteria now. So in some cases, chlorine will not work. Like sulfide reducing clostridium bacteria, chlorine is not working. But ferrate does work. So ferrate can also be used as a disinfectant. And this is the example, and it's better than chlorine. Okay? And it can also work for COVID virus. You just, this virus is easy for ferrate. This is not my work, it's from literature. But they have shown, you can see this here and goes to 0. This is FR, this is like Fenton reaction. And but it does work for hospital wastewater. They have shown, so it is bacteria and virus, it really works. And it can be used in hospitals. Not only in water, it can be used in hospitals. You know, hospital, I don't know about this country, but US 80% market is chlorine-based products. And have you anybody come across chlorine in your life? Bleach. How does it smell? Imagine situation, if something is horrible, you think you will use properly? So that's happening regular basis in hospitals. And if you don't use properly, because of just smell, many other things, you get infection. So that's what I visited. One time I proposed to National Science Foundation, I want to use ferrate for hospital disinfection. And they said, really? I said, yeah. But then say, don't sit in the lab. Go around and visit hospitals to really think it will work. First find the problem, it has a market. And I did. And this is what I learned. It destroys bed and furniture, not only smell. And if you don't use properly, then you acquire infection. So if you don't have to go hospital, just don't visit. Use Ayurvedic. So don't go. See, for surgery, people go for surgery, then they have to go back after surgery because they acquire infection. And see how much money they spend. This $70-80 billion per year. Okay, so but ferrate works. So ferrate works finally not only for hospitals, but also it works for vegetable fruit. That's also, so this is really fresh spinach, fresher. Bacteria are on the surface of this vegetable destroyed. Gone. Okay. And you can use, so basically we apply for patent. We have a patent issued on this one here in US. And this is what I was talking with Parveen. This is Chetan Tata. He's the one, he's from Karnataka. He's the chief infection disease. So Karnataka people always help me in this my journey of this career. And I called him real doctor. Yes, sir. Sorry, yes, please. It's just like a bleach. Toxic in the sense that you will not drink or it should not do that. That will is oxidize. But other than that, it's just like a bleach or less. So I call him real doctor. You know what I call him myself fake doctor. Why fake doctor? PhD. Do you know what's the meaning of PhD? Somebody know Hindi here? What's the meaning of PhD? Huh? P means fira, H means hua, D means dimag. Fira dimag wale log hain hum. So I'm not real doctor. So is this true? You ask any questions to PhD, they never give straight answer. Yes or no. They create a problem and they solve that problem, feel happy. That's their life. Okay. So you can see many data. We can remove many resistance bacteria, E. coli, and using this ferrate product. So he's the one who helped me. Chetan helped me. He's the chief of infection disease in this hospital. And we got very interesting finding, discovery. That is, you know, in medical doctors in US, they really make good money. And he has his house is here in very Lake View here, and he collected water from here, and we killed the E. coli there too. And not only this, you can toxins also, like a microcystine that you see green water, algae grows and release toxins. It can destroy that too. Other toxins is cylindropomopsin. These are the things. This is a big problem in India too, all over the world. Coastal water, people like to live close to water, a lot of nutrients, this, and they create all kind of toxins. And they release toxins like this. So ferrate can remove. This red color is showing by method HPLC is being removed. And we also tell everyone not only remove something to make sure what you're producing is not toxic. Okay, so here we test the toxicity. At least in this ILSA method, didn't find any toxic product after removing this CYN, this toxic. Now we also tested this one for removing pharmaceutical and personal care products from wastewater. Okay, and is the real wastewater. And what we found, good news and not so good news. Instead of bad, I say not so good news. What that means? Good news is most of this we are removing 100%. And not good news is some are we are not removing 100%. Clear? And I like to call myself real Iron Man. What that means, real Iron Man? I can solve any problem. Right? So I will tell you the story how I'm trying to remove pollutants, all pollutants. Okay. To do this thing, I need to go to the chemistry, very basic. Iron exists in different oxidation states. Iron 0 valent, which has D8 electrons. Okay. Once you remove 2 electrons from it, it becomes ferrous ion. Once you remove 3, it becomes ferric ion. These are naturally present. Clear? Now, if you want to remove more, you need to synthesize. D4, if you remove 5, becomes ferrate 5. If you remove 6, becomes ferrate 6. If people could do it this, why not 7? Why not 8? Nothing wrong in dreaming. Okay. So how I understand these ones? Here is like it happens, I try to learn this one process. So what I'm trying to say is this one. If you understand this one, you will maybe discover something new which I never thought. Okay. So I'm taking this 6 going all the way to Rn2. Okay. You can do 1 electron, 2 electrons, and I like to control things. Right? Human nature try to control things. We don't like which we cannot control. See, some pollutant you cannot react or you cannot remove by 6. I bring this 4. If 4 doesn't work, I'll bring 5. Just like going to head chair, dean, and director. Director will really slap you. Okay. Same thing, 5 will slap you. Okay. And how this is very important. Okay. So this I'll show some examples. Okay. And I also like to convey once this is formed, but if ligands are around, it will form complex. I don't know, I'm just postulating it form complex. But whatever, if complex is there, surrounding is by ligand, this 4 or 5 behave differently than this one. Okay? And I want these ligands are natural ligands, which are interfering in my treatment. So I'm taking advantage of those ones. Rather than inhibition is doing, I want to harness those ligands, like carbonate, organic matter, so I can take advantage of those ones. Okay? So I'll show again examples. So again, just to show that 6 can do in minutes, but 4 can do in seconds, 5 can do in milliseconds. I start calling this activated ferrate technology. And this is ferrate technology. Goal is again, saving lives, even one life. That's my everyday motto. Here is just to show example. Sulfate, they behave like a single electron reductant. So you can react with 6, and this one produce 5, and 5 can do the job of removal in 30 seconds of these pollutants. It's the pharmaceuticals. Okay, 6 is not doing much. The moment you add sulfite, it can do in 100% removal. Same thing, these behaves like 2 electrons, and you can do in 10 minutes of these ones. And then you can also use this for different kind of bacteria viruses, because the way things are going, human behavior is going, we are not going to change. Bacteria virus will keep coming. The nature has its own way of doing things. If you look the structure of, to me, I don't know about you, COVID virus, so complicated structure. We're synthesizing naturally from somewhere. So I'm going to start giving examples of this. I showed without ligand, but I'll show you the example with the ligand now. So I'm going to start giving examples of this. I showed without ligand, but I'll show you the example with the ligand now. So prolonged antibiotic resistant bacteria environmental. I'm an environmental chemist, okay? And there's a big problem, antibiotic resistance bacteria and genes, okay? I already mentioned that. And because bacteria is adapting, antibiotics, we take a lot. You and I took this morning, okay? Sorry, my voice is because of this cold. And the moment you go to doctor says something is not working. Doctor will give you more antibiotics, and you feel good. Or patta le lo. Okay. So this is a big problem. And you know, the moment we take pharmaceuticals, more than 60% come out from urine. It doesn't get metabolized. Once we have more antibiotics around in the world or environment, we have more problem of antibiotic resistant bacteria and genes. And that's why this agency is saying this is one of the biggest global health crises of the century. Okay, and I'm not making up to get more money to funding. Okay, so it's real problem. Why it is real problem? We are not producing new antibiotics, and that means antibiotics, no new antibiotics, bacteria will appear, and no antibiotics will work, like COVID. I cannot read either. I'm just scaring cartoon. This is just can convey the math. Yes. Is it here? Is the molecules in water that is showing here. Okay. I have to read this, but that is this human acting health of the system. Okay. No antibiotics because no. And what is going to happen? Government will spend a lot of money. So I like move antibiotics from the urine itself rather than it goes to the water, get diluted. That's more difficult to remove. Okay. And urine has lot of nutrients. Okay. Once it has lot of nutrients, you can capture those nutrients maybe, create a fertilizer. India has a crisis right now, fertilizer. I don't know how big, but there's a shortage of fertilizer. Farmers are asking fertilizer. You know what fertilizer comes from? Most of in the world? From Russia and Ukraine. They're fighting. Food security problem. So maybe we can create remove antibiotic from urine and recover the nutrients. And what we try to do, use ferrate. First, we want to know what is the urine contained. These are composition of hydrolyzed urine. Some are the salt, and some are organics, creatinine, and uric acid, and some salt. And we learn, yes, now is a healthy. Is urine. Any question? They are afraid of you the moment you said somebody's asking. I afraid of you. Okay. Yes. 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 You're creating a lot of salt. Okay. And so what we did, we tried to use ferrate in combination of these different salts. Okay. And we learned something new. Once we have carbonate in the solution, our rate of the reaction is increasing and also linearly. Nobody saw this before. Yes. It's not only unique to India. Well, they are helping all these doctors, right? So they also need jobs. We have too many medical colleges in India. So some have no degree, but they are still doctors. Yes, their study came out, by the way. There's some real, not medical degree, but they have shops and everything. And Himachal, where I came from, I was reading yesterday, they don't have even good quality of drugs they produce. They're failing. That they don't, people lose jobs. It's so simple to control the quality. Nobody buy drugs from India, right? Or somebody, they lose so many jobs. So simple thing to do. Control the, but that what you get a hydrolyzed urine. No, no, no. You see here pH 8, we have done pH 8 too. The slope get bigger. Okay. Carbonate and ammonia. This is ammonia. Ammonia also increase, carbonate also increase. And then we also tested these organics. And out of these, this organic is also enhancing the rate. They don't do much, but this enhance it. Okay. And you can see the structure of this. It has nitrogen in the ring. Okay. And we get ambitious. So we get ambitious. We did many amino acids, all essential amino acids. We found proline is the ones enhancing the removal. And again, that you see nitrogen in the ring. So somehow this organics which have nitrogen in the ring, that's something. That's very important. And if you think inside our body, we have enzymes, right? Enzymes have this kind of structure. So nature is doing very nicely every day. When I show these slides, or yeah, this slide, I ask the question. To me, it's fascinating. When I say fascinating, doesn't mean it's fascinating to you. To me, it's fascinating. What happened to oxygen when we take the oxygen and breathe? What happened to that oxygen? What gas? We need oxygen, right? What happened to that oxygen? It remain as oxygen? where does it go? Such as, mhm. So which glucose take oxygen? Uh-huh. Right? Sorry? Hemoglobin. That's what you said, right? Uh, RN in the hemoglobin, oxygen, right? Have you seen hemoglobin structure in your life? Very complicated. RN is surrounded by this lot of proteins. Yes, but is ready to give those electrons to oxygen. RN is so happy out of jumping those electrons, passing through those big proteins. Very nice. Nature is doing it. We should learn how they are. They do 24/7 very nicely. So don't disturb this mechanism. Don't get stressed out. Okay, that disturb the mechanism. That's where you get disease. When oxygen is coming, let it breathe easily. Take that electron from the RN, and it 4 electrons to convert to water. How they're giving 4 electrons? I think it's not fully understood. The person who understands, they make a lot of progress, will get the Nobel Prize. So you can get the Nobel Prize if you understand this, how this happens. Okay. Other things we found with ferrate, that this is natural. As you see, this rate is increasing of this pharmaceuticals. Because it's something natural organic matter is helping. That committee recognized that one. I was not sure if my paper will explain nicely, or because I'm talking something different, unconventional. And this is good prize. I don't know if you heard this prize before. Yeah. Oh, thank you. Thank you. Why is he giving congratulations? That they give the money. And money. He still wants to know. But I think it's a nice thing which I am very proud of myself. The money comes, people get greedy, right? And for you don't do things yourself in your life. Along the way, many people help you. So including this doctor I mentioned, Konstantin Data, and 2 others, one from Radik Zibrov from Czech Republic and a Georgia Tech professor. These 3 helped me along my more than 20 years. So I share the money. Okay? I divide equally. It was under my control. If I give or not give. It's 2, they even didn't know that I put the name there. And total money was $133,000 is your personal money. So I divide into 4 and gave those $32,000 to each one. And I get 32,000. And my wife did not complain. So very nice of her. So let me do that. It's not easy, but she was very happy. I got award and then I shared the money. And so far, I get close to, I don't know how much time I have, but I start here to here, right? And you can see I'm interested in these ones, right? And one day, I a catalyst, so I can create 4 and 5. And that's what the professor can help me to synthesize, which can have 4 and 5 catalysts, because then I don't need to add any chemical. I can use oxygen, use the material, create 4 and 5, and get rid of chemicals or pollutants. That's my dream. And again, nature is doing it. They are doing from RN2 to RN3, produce these ones. Our body does produce these ones. I think, no evidence yet, but he will create that biosensor to prove it. And then we both publish in Science. Okay? No, seriously, I'm still talking seriously here. Okay? Even I think is atmosphere, aerosols, they also get produced this one. Ocean also produce this one. But nobody pay attention. I want to pay attention because I have nothing else to do. Okay. And Rn2, Rn3 produce this one. Let me talk how I'm producing this thing from there to here. So I understand the whole thing. One is historically, this was, you can see my PhD mentor, Frank Milaro. And remember that beach lab, okay? Rate is increased by carbonate ground. I already showed for high-valent Rn, right? And here is even low-valent with oxygen, it's producing. This rate is increasing. Nobody knew before. They ignored carbonate. But we showed recently, this is Ashwin Vijay at Ariel University. He's from Kerala. He's a professor now or in Poland. And Dan Meyerstein, he's close to 90, still writing proposals and publishing paper. And he told me, it's not easy. So I was there 2 weeks ago with him. And we showed carbon radical, don't ignore carbon radical, or carbonate in water or anywhere. And here is I tell, if you don't know why it is happening, give many, many equations. Confuse people because you don't know the answer. And then hopefully paper get accepted. Okay. For carbonate is using carbonate radicals, not this sulfate. This is historically people doing it. But please pay attention to carbonate. And we did many other metal science. And I'll skip this one. But other important things to show, we did this reaction of perovskitic acid with Rn3. And we tested many ligands. And only one ligand shows the reaction become faster. Again, that is this one, phenolic acid. Again, it has nitrogen here. Again, back to nature. And we have done on manganese high other high-valent 2, not only Rn. And we did ruthenium. Also, ruthenium is fascinating. I'm just getting interested in ruthenium. As a catalyst is fine, otherwise it's expensive. Here is other important thing is we have done. We have used, here is a lot of improvement in need. Okay? Your material can do amazing things. We synthesize titanium-based photocatalyst. Okay? What it could do for, this is like a metal organic framework, it can remove fluorocompounds, even in presence of oxygen. How that happens, I don't know. Remember, I was saying oxygen is the problem. Okay? But here, even it works under electron, sorry, under oxygen. And that's what this paper showed, that this can be used to remove fluorocompounds. I'm also interested in single atom I mentioned. And this, basically, I want to create single atom catalyst, produce this high-valent metal species, which I can try to convince these are better because they are inert to ligands, natural ligands. They are helpful. And that's what this slide is showing too. And so far, real sense, I haven't produced any paper. There are a couple of papers, but not big ones. But I wrote a review, tutorial review. If you're interested in a single atom, please read this paper and cite too. And again, this is other collaborator for more than 20 years. Tough guy, Radik Zibrov. He has many Indians. If you're looking for postdoc, apply. Maybe he has money. Okay. And spell is sensors, environmental. He's weak, I think, environmental. And I'm very thankful to him. It made to the cover of the journal. Why I'm thankful? Because he paid for that cover. Okay? Is it a charge? Not cheap charge. Paying. You know, impact factor of the journal? When I submitted a couple of years ago, it was 60. Now it's probably sitting around 40. And I'm interested in what is the fate of plastic, nanoplastic. And this other editorial we have written, nanoplastic are potentially more dangerous. Again, you need to make sure you say dangerous. Otherwise, don't get the money. Okay. So nanoplastic, I'm not only interested in to collect. And not only, remember, I monitor and solve the problem. Okay? So I want to create some kind of methanol, ethanol, or formic acid, and you can do it because they are very highly reactive species. I learn enough about these ones. This is my vision, create some nice water, lemonade, put ferrate, go to rural areas, tell them, put some ferrate, little bit, they put the lemon and ready to drink. Some books, here I like to thank my wife, that's created by her, or not, Alice, she gave the idea. So please say you like it, okay? It's very important. Thank you. She's, oh, I'm very, yeah. So this is her idea is like ferret is trying to save the globe, Earth. And then 4 and 5 are floating around how they can help. Moss Bauer, I don't have time. These are my of this book edited on Moss Bauer. You know Moss Bauer, have you heard Moss Bauer spectroscopy before? Okay. So the story. Take one statement, partial statement. Please pardon me. But don't listen. His boss told him to his spectroscope. So don't listen all the time. So, so they are going for Nobel Prize then. I don't need to tell them. This is the book I have written to honor my mother who passed away losing a lot of protein. So I read why person can lose a lot of protein to radicals were produced in our body. And whatever money I earn, I create endowment and give to Fairly Woman award every year. I think these are funding agencies, and this is the time to say thank you and dhanyavad. Don't be shy. I'm here. I came all the way. Don't disappoint me. Yes, please. Yeah, tell my boss, please. Send email. So I have a job.
So I just one doubt. Like you said, chlorine. When it so does that get trying to?
So first thing is we do need to add excess chlorine. Is meant to be because during from wash treatment plant come all the with tap water, there's a possibility bacteria viruses. So they add excess. So it doesn't happen when it goes to there. Okay. So so even that's why in water you see excess of chlorine. Sometimes smell chlorine in the water. That's the That is the reason. So ferrate probably needs to be combined at when it goes because ferrate will not last. We don't want people to drink ferrate, right? So after the treatment, you still need to add a little more chlorine. Ferrate will not be there, so it will precipitate out as RN3 immediately in water. It leaves the treatment plant. Yes, cooling down. Yes, magnet. Yes, because we did with arsenic, we showed the magnet can be used. Our graphical abstract has magnet to demonstrate it works. You're very welcome. Yes, please, from the back. Otherwise, ladies exam, it will not be pleasant. I call the parents. No more hugs during holidays.
Sir, when you are that it help to degrade the organic molecules, right? So, how commercially how it is feasible in water treatment? Like say you have a 80 gas, okay, and you need I need to reduce it 0 or let's say high ppm. So, how much ferrite we have to dose to reduce part ppm of the gas or any ferrite compound or any organic? Is it commercially viable with respect to the present?
Question is, if you want to remove your expansion, that always we can
In the chemistry, the industry, when we are talking about the commercial industry, have to speak about the industry.
yes.
So let's say they have some wastewater, okay,
Mm-hmm.
and they will never tell you what is in their wastewater, but we can assume that from their product, we can assume that this may be the possibilities of the organic present in their wastewater, right? So it is just by considering. So let's say your wastewater contains certain amount of organic level, but along with that, it contains tar or any oils. So in this effective, the water contains tar or oils. Yeah, basically higher.
Yes, you need to add possibility of start the molecule ferrate 6 to make it happen. And hopefully the RN3 that had also hydrocarbon to something else, it needs too many electrons going all the way to carbon dioxide. So it's better to just move quickly and do something, convert into something that's useful. Please keep up.
Yeah, and I have two questions.
Yes.
So regarding these chlorines and all the carbonate sulfate created in the water. So let's say I have a water which contains the sodium chloride ion, okay, and I am using this ferrate to remove the chlorine. So does it mean it will reduce the
You mean chloride or chlorine? Chlorine, Cl minus.
Cl minus.
You want to remove that?
I want to remove that. So does it work?
No. No, chloride is just the salt ions, right? You need to use, you're talking desalination.
Yeah.
Okay. This is not, this is chemical process. Desal is physical process. But it can help you because once you, I'm talking something different now. When you do desalination by membrane, right, this falling is, it will not allow to create that problem. We make membrane more efficient. Okay, I'm giving something different answer. But chloride with desalination, that's totally different game. That's physical, not chemical process. Israel is very
Saw that for the for with respect to the for Fenton process, it will take much more time to degrade the organic molecules. Let's say for 100, I'm just assuming that let's say 100 ppm we have, it will to go to the 0 ppm, it will take us 60 minutes for a specific organic compound. So how fast the ferrite will do the same degradation?
wait. Here is the, I think I didn't spend time. Fenton reaction, I have a lot of interest in Fenton reaction because Fenton reaction has itself is the issue. People don't understand Fenton reaction. We are trying to convey, this is the Fenton reaction, okay, where Rn2 react with H2 to produce OH radical. And efficient at pH 3. So imagine you're doing very acidic any treatment. You're destroying the environment and still create a lot of sludge. And once you get neutral pH, doesn't work. And reason is that instead of this, it's using carbon radical or Rn4. So back to your original question, is 60 minutes taking even at pH 3, which is efficient. Other is OH radical is not attacking only organics. It will disappear itself. That's by definition OH radical, right? That's why it's taking too long. Because steady state concentration of hydroxyl radical is not high. It's low because dissipating itself too simultaneously. And some organics, those are tough ones. And actually OH radical create more problems. You can remove phenol, but you're creating hydroxyphenol compounds. They become more toxic. So OH radical is not the solution. That's why you don't see much Fenton reaction used in real environment to solve the problem. So in some cases, you can use to satisfy some regulating agencies. We are done. We remove the phenol, or we remove this one here. A real sense is you need to test the toxicity. Okay. This side's asking, what's
basically, sir, thank you so much. Change the microorganisms to become resistant to it, bacteria. What would be the same when excess of ferrite or whatever parts?
in let's say after 40 years, 50 years, we don't know. History of ferrate and chlorine, they behave differently. That means it, and they those like cysteine and those. So yes, somebody was asking. Yes, go ahead. Please. So,
My question is very general because I am asking this question. I am belong from village, so where we were drinking water without purification process. So why we need to clean the water? And what is the base problem of cleaning the water?
okay. Mainly, water see the
And also, sir, using purification, we were also losing some irons, those who are base minerals. So
oh, oh, okay. Thank you very much. Have a good day. Happy New Year. Enjoy your life and care about the oxygen. Oh, take photo, please. Send me the photo. Oh, thank you so much. Appreciate that. Oh, thank you. Very kind of you. Very, very nice. You can take it out poster. We have time. 1 minute. Poster may be more important than flight. What about taking? I can sit photo with everyone. I sit here. You can take. Yes, please. Yes. Should not forget. Take with me.